In this video, we're going to study k permutations. A k permutation is a sequence of k letters, all taken from the same set, with the requirement that distinct places get distinct entries. That is, for all I and j, if I is not equal to j, then ai is not equal to aj. So for instance, if a is the set 1, 2, 3, 4, and we set k equal to 2, then we can actually look at all the possible k permutations. Namely, an example of a k permutation would be 1 followed by a 2, because these are distinct, or 2 followed by 1, because they are also distinct, so no order actually matters. But 2, 2 is not, because the first and second coordinate are the same. In a higher example, if I set k equal to 3, then you see that 1, 3, 2 is a valid sequence. That's a k permutation. Or 4, 1, 3. But 2, 1, 2 is not, because it has a repeat. So no repetition is allowed, and order matters. That's the definition of a k permutation. Naturally, the next question you ask is, how many k permutations are there? Well, it's going to depend on the size of a. And for now, I'm going to assume a is the set of positive integers 1 through n for some n. So how do you specify a sequence of length k? Well, you have to specify the first entry, the second entry, the third entry, all the way through the kth entry. Now, once you've specified the first entry, you see that the second entry can be any of the numbers except the first, because if you choose the first entry again, you now have a repeat. Similarly, the third entry can be anything except whatever you picked for the first two. And in fact, since these two are distinct, this set really has size 2 here. Similarly, A4, you can pick from everything except whatever you chose for the first 3, and so on and so forth, up until you get to the kth last term in the sequence. The last term in the sequence can be anything except what you chose for the previous k-1 terms. And again, because we are assuming these are all distinct, this set right here actually does have size k-1. And so in general, you see that on the ith step, you're choosing everything except what came before. And so how many possible choices are there? Well, there's n minus parentheses I minus 1. The n possible options take away the ones that you can't pick. And so this is, when you distribute the negative sign, this is actually the same thing as n minus I plus 1. So if I plug in k for I get n minus k plus 1. And so the number of k permutations of n is this product n times n minus 1 times n minus 2 dot 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 all the way till n minus k plus 1. If you like factorials, this can actually be written as a ratio of 2 factorials. N factorial divided by n minus k factorial, where n factorial is the product of the first n positive integers. In some lectures, I will actually use this notation for it, n to the k underlined. This is called the falling factorial because of this formula. And so we see that this is the number of k permutations. And what we were going to prove at the end of the video is that the number of k permutations is also the number of one-to-one functions between two sets x and y, where x is size k and y has size n. So in this example, let's do some calculations of these numbers to get used to the calculations. 4 falling 2 is 4 times 3 minus 1. 4 minus 1, sorry. Of course, there's a typo on the very first calculation, which is just 4 times 3, which is 12. Similarly, 15 falling 3 is 15 times 15 minus 1 times 15 minus 2. And the way to keep track is that so that's 15 times 14 times 13. And now you start to see the pattern. You start with this number, and you keep decreasing it by 1. And you multiply all these numbers together, and the number of terms in this product is this 3. So 4 to the falling 4 should be 4, 3, 2, 1. Oh, look, that's 24. In this case, that actually is 4 factorial, as it should be. So one final calculation, what if you do 3 to the falling 5? Well, according to this formula, it's 3 times 2 times 1 times 0 times negative 1. If you multiply anything by 0, you get 0, which should make sense here because if you look at this in terms of permutations, you've got 3 letters and you want to have a sequence of length 5 here. So for instance, if my set is 1, 2, 3, I want to have a sequence of length 5, so I have to pick A1. Suppose I pick 1. Well, A2 can't be 1. It has to be 2 or 3. Suppose I pick 3. Then I see A3 is forced to be 3, and I see A4 is nothing. There, I've run out of room. So if the length of the sequence is longer than the set, and you're requiring the entries of the sequence to be distinct, you see that there are no such k permutations. And that actually matches what our formula tells us too. Okay, now we do some word problems. So how many ways are there to pick 3 movies to binge watch out of a set of 12 movies? This would also be a problem that would pop up if you wanted to pick your favorite 3 movies out of a set of 12. Here you see order's supposed to matter because naturally if you're going to pick 3 movies to watch, you have to watch one of them first and you have to watch one of them last. So there's 12 ways to pick the first movie. Assuming, of course, that you don't want to watch the same movie twice in a row because that would be psychotic. There are 11 choices to pick the second movie. And then finally, to watch the last movie of the night, there's 10 choices because you don't want to watch the movie you watched first or second. And so this is the answer. And as I've mentioned in class, to me this is an acceptable formula. A full correct answer would actually point out that this is equivalent to studying the set of 3 permutation of 12 and then just quoting the formula and calling it a day. Another example of a problem like this is how many ways are there to give 3 colored marbles to 4 kids, with the restriction that no kid gets more than 1. It's not clear what this has to do with k permutations yet, but it turns out it does. So, of course, I should be pointing out my implicit assumption is that these are distinctly colored, namely red, green, and blue. Actually, for the colorblind folks, let's use black, green, and blue. And that should be, or black, white, and blue. That should be distinguishable. And let's have 4 students. So suppose these are the 4 kids. And well, how could you consider all these distributions? Well, you could ask yourself, who did the black marble go to? There's one of 4 choices, right? And so that gives us the first 4. Once you've given the black marble away, you see the white marble can't go to the same person as the black marble went to because then you violate this restriction. So for the purposes of argument, suppose that the black marble went to Bob. Then we see there are 3 options left for the white marble to go to. So 4 times 3. And then finally, once you've picked the person who gets the white marble, say 1, then the blue marble has to go to one of the remaining 2 people. And so we see, even though this problem doesn't look like it has to do with permutations, it actually does. So distributing distinct objects to distinct people with the rule that no person gets more than 1 prize turns into a permutation problem. And so we see the answer is 4 times 3 times 2, which is 24. Finally, we end with an actual math problem. How many injective functions or one-to-one functions are there from a set of size n to a set of size k? So here's worth pointing out. Sometimes I use square brackets n to represent the set of positive integers 1 through n, square brackets k to represent the set of positive integers 1 through k. And it is worth pointing out, how could you actually determine such a function? Well, look at the graph, essentially, or look at this sequence. So given the function, create the sequence f of 1, f of 2, all the way up to f of n, and then see what you get. So here's an example of such a function. From 3 to 9, you see that it's 1 to 1 or injective because distinct points in the domain are mapped to distinct points in the codomain. And under this construction, we see 1 goes to 2, so the first coordinate is 2. 2 goes to 4, so the second coordinate is 4. 3 goes to 6, so the third coordinate is 6. So you see the idea is, given these injective functions, once we look at this sequence of outputs in order, you get a sequence with distinct entries. And you see that's true in general, because the only way you have a repeat is if you have 2 points in the domain that map to the same point. So essentially, the number of injective functions is equivalent to the number of sequences of length n with distinct entries. In other words, these are n permutations of k, and so the answer becomes k to the following n. So here I made the mistake of changing the notation, but it's worth pointing out sometimes the notations change, so you always have to keep track in a given word problem what n corresponds to and what k corresponds to, because they don't always correspond to the things that they do in the general formula. So we see the number of one-to-one functions is actually equivalent to the number of k permutations, and so it has the same formula.